So here we have furnace wall with the thickness of X equal to 0.3 meter. Thermal conductivity is given with 1.2 watts meter Kelvin. The heat is conducted through the wall, okay, and then after that it is divided into two, which is radiation. So after conducting heat from here, from point 1 to point 2, it will be then transferred by a radiation Q, and also there will be convection. So H value of the surrounding air is given 20 watts meter squared Kelvin. The temperature of the surroundings is also given 27 degrees Celsius, and what is to find basically is the temperature of the source. So 120 degrees Celsius is given in this part, external wall. So solution. So again, this one is energy conversion. Energy in equals to energy out. The first energy from this point is basically the heat by conduction, and then it's divided into two, heat via convection plus Q via radiation. The formula for again the conduction following Fourier's law, that is K area T1 minus T2. Actually this one is negative, but then since we first put the higher temperature in this side, so we can write this as positive, over the thickness equivalent to heat transfer by convection is given by HA multiplied by T2 now minus T3. Again, T2 is the surface temperature here, 120 degrees Celsius, plus the radiation. So emissivity factor multiplied by Stefan Boltzmann multiplied by the area multiplied by the absolute values to the fourth temperature. So T2 to the fourth minus T3 to the fourth. So again, here we have common area will be simply cancelled out, area, and then take note T1 is the unknown, T2 is given 120 degrees Celsius plus 273. This must be equal to 273 plus 120. This one is 393, while this one plus 273 is around 300 Kelvin. So T2 is given, T3 is given, H value is also given. Emissivity factor is, this one is given 0.8, and Stefan Boltzmann constant given, T2 is also given, and T3 is given. So we have one equation, one unknown. So in this equation we can simply substitute all the values. Thermal conductivity K of 1.2, okay, 1.2 watts meter Kelvin multiplied by the change in temperature T1 minus T2. T2 again is 393 Kelvin over X, that is 0.3, the thickness of the wall, equivalent to H value is given 20 watts meter squared Kelvin multiplied by the change in temperature 393 minus 300, this must be in both Kelvin, plus heat by radiation we have 0.8 plus 0.8 multiplied by Stefan Boltzmann constant 5.67 times 10 to negative 8 watts meter squared Kelvin to the fourth. And then here we have delta T. T2 is equivalent to 393 raised to the fourth minus 300 raised to the fourth. So unit analysis, here we have Kelvin in here, so watts will be cancelled out, watts. Here we have meter multiplied by meter is meter squared, that is denominator, it will also cancel out. So this will cancel out. So we have here only Kelvin as a unit of temperature, T1. So T1 is blank terms of Kelvin. So here 1.2 multiplied by the unknown alpha X minus 393 over 0.3 equal sign. We have 20 multiplied by the change in temperature 393 minus 300 plus 0.8 multiplied by 5.67 exponent negative 8, 5.67 exponent 5.67 exponent negative 8 multiplied by the absolute value of temperature to the fourth minus 300 raised to the fourth, and then we close, shift, calculate. So for the x, we have 1036.65 in Kelvin, but take note, we can simply subtract 273 in here, so minus 273, and you have 763.66 T1, basically 763.66 degrees Celsius. So the answer is letter B.